This is, yeah. Yeah, okay. Hello, everybody. And this year I will continue my talk of last year, where I showed how to switch on and off GPIO pins. And this year I will use some applications where I use more than one I/O pin, and this is especially the I2C bus chips and the SPI bus. And here again on the slide you see the pins of the Raspberry Pi, and I want to mention again that you never should put voltages higher than 3.3 volts to it, because this would damage the chip. So the first demonstration I want to make is with the I2C bus, and here I want to greet also Gerhard Reithofer, who also had had an article in the wiki, and he was maybe the cause that I did my talk here. It's my way, what I do, but he was maybe initiating my talk with it. So you see here that the I2C bus needs 2 lines, the serial clock. It's connected with the line 3 of the GPI port, and SDR is the serial data that is on the pin 2. And well, I use yeah, we will see later. I use only nowadays 3 LEDs here, because the others are not connected. But the photo is from the last year, so you see here 3 LEDs. So the demonstration I want to show here, it takes some programs to run. 2 programs must be run on the Raspberry Pi with the starting I2C as a script that will export the GPIO pins that I need to use. And then I have a little server 8888, which is listening on the Raspberry Pi and receives some short one-line commands from the computer to put, for example, the SCL line low or SDA line high, and so on. And on the computer there is Wish I2C demo. This is the program where I will show a demonstration of the I2C bus. So let's try it. Yeah, I put this off, this on. This is strange. Yeah. As first, I have to go to the web browser. In this web browser, after the start of the Raspberry Pi, I get this message, list help, press button to get help. This is just the starting thing. And as I mentioned in the slide before, I must first now do the starting I2C, E.C, and start and send it. Ooh. This is always what is demonstration. So, cross my fingers, now it works. And as an answer, this script starting I2C gives back the was heißt Verzeichnis? Directory, the content of the directory. And now you see normally when there's no lines exported, we don't have these GPIO 2 and 3, so now they are active. And the next thing is I have to start the server, and I load the script server 8888. Now this is really a very tiny server, you see. It's just a minimal server that I found in the EuroTcl wiki, yes. And I have to start it by exec-tcl shell as I start a background process and I send this command to it, and now we have a background process, and the process number is 2629. This is not of interest now. Yeah, now I can hopefully now connect to my Raspberry Pi with this I2C demo. Yeah, it works. And to see what happens on the Raspberry Pi, I have a camera picture which shows the LEDs. I have to move this a bit. Yeah, on the right side you see the LEDs on the Raspberry Pi that will do something afterwards. So my demonstration program is a Tcl script that will exactly do what is done on the Raspberry Pi. The initial state of the I2C bus is that the SDA line is high and the SCL line is high, and I can do short steps, long steps, and so on to go through a sample program. Also, one state of the I2C bus is that you send a start command, and the start command is that while the SCL level is high, the SDA will go down. This makes a start, and then next affair is that you must address a chip on the I2C bus and send 8 bits from the I2C bus. And the first bit, in this case, when I send the chip address 64, which is decimal numbers in this case, is a 0. 0 means that the clock signal goes low, and yeah, this was a start command. When it is low, then the serial data must be set either 0 or 1. In this case, it is a 0. And when the serial clock rises, then this 0 bit is then sent to the chip. And now I make long steps, so I will produce several bits at a time to show how this works. It's not very fast, this demonstration, but so also I sent first this chip address 64, so this is 0, 1, 0, 0, 0, 0, 0, 0, and then when I send 8 bits, then the chip that is addressed must resend an acknowledge bit. So I send on the serial data line, I send a high level, but the chip pulls the data line down, and so it acknowledges that it has been found on the bus. Next, I send the data, and the data was I send a 2, I send a 4, I send an 8, and every time I send it, then you observed maybe that the LED was switched off. So it is in this demonstration, it is like this, that when the data has a high bit, then the LED will be pulled down and it's off. And when I send a low bit, then it is on. This is so because the LEDs must have a current of several milliamperes, but the I/O expander that I use have only a weak high-level capability.
Driver. High driver and low driver.
Yes, they have a very weak driver capability when it is high. So I inverse it, and so the last bit that I sent was an 8, so it's 1, 2, 4, 8 in this level. So only this one LED is out, and the other LEDs are on. Yeah, and when I send a sequence of data to the chip, and I want to stop it and send data to another chip, then I must do a stop procedure. And this you can maybe see how the stop is. The clock is high then, and the data will go high too. So this makes a stop signal, and then the bus is free for new communications. So the next will be address now on another chip. This is the 66, and you saw maybe that here the 3 LEDs from the other chip are now off, on, yes, and because I sent a 16, a 32, and a 64 to this chip. And now remember the first chip with the address 64, it had the data 8, and the second chip has now the data 64. In the next demonstration, I will now receive data from a chip, and this is then I have to send the read-write bit, which is the 8th bit, must be set. So I get the oh, what's that? That's not correct. Now I send a 67 because now the read-write is high. And the chip receives it. But this is maybe because I have this plugged in. I have maybe to restart it again. Long steps. Yeah, so this was the first chip. The second. Okay, this. And so you see, when I want to have the chip in writing mode, I send a 0, and when I want to receive data from a chip, I send here as an 8th bit a 1. So let's hope that it will now correctly find the data. Yeah, now it works. So I sent before the 64, and it is now in the register of this chip. And when I read it, then I receive also the 64. And when I receive a byte, the master receives a byte, it has to send an acknowledge itself and pull down the 8th bit. But when it sends a not acknowledge at the end, then it signalizes that the sequence of receiving data ends, and then the chip that sends the data back to the master will then only retire from the bus and make only high-level bits because it is no longer responding. And this effect permits the master also to send a correct stop signal, because during the stop signal the bus must be in high level, and the master must be able to pull down the data bit and to move it up again. If this is not the case, as I show in the next slide, is when you do not, the master does not acknowledge, then, for example, here I now want to receive the data from the other chip. This is now here, instead of 64 to 65, so the read bit is set, and I receive 888 all the time. But now, when I try to make a stop, the receiving chip, 67, pulls down the line always, because it doesn't think that it should retreat from the bus. And so instead of that the stop condition occurs, the receiving chip only sends the next first bit from it, and no stop occurs. And when I continue, then I get nonsense on the bus because the line is always low, and the chip thinks he shall send data. It sends also the data and acknowledges it, but it's not that I start a new communication. So it's not the right thing. Yeah, and finally, yeah, it sends nonsense. So I have to somehow restart until the stop condition works again. In severe cases, I have really to power down the whole I2C bus and restart it, so that all the chips make a reset and that the communication works okay. So well, I hope you could see a bit how the I2C chip works. The next demonstration I want to show here is about the LCD. Ansicht, presentation. And in this demonstration, I want to connect an LCD chip, LCD chip on the I/O bus expander. The I/O bus expander has 8 pins for communication with other chips again, and I use pin 0 to 3 and 5 to 6 and 7. And on the LCD module, it has 14 pins normally, because the LCD chip normally communicates with an 8-bit bus, but we can switch the LCD chip to 4-bit communication, and then we have 3 handshake lines. This is the enable pin, the read-write pin, and the read or read to display or read to RAM pin. And the data pins are only 7654. There are only 4 data pins. And 3 pins here. This is here. They are just for providing the chip with power and do the contrast of the LCD also. So I have to plug it in now. No. Ay, ay, ay. So and now I have to do another demonstration. This is a LCD demo. And I move the camera that it shows the LCD display here. So in this case, I put the bus to 0, and then I power the LCD chip on, and when I power it on, no? Yeah. Then I have to send to the chip some commands. Well, the first command is that I have to switch to 4-bit mode. And then all further instructions that are sent to the LCD chip are only put by 4 bits, not by 7 bits. Then it will switch to one line 4 times 8 pixels. And by the way, I need always, for one instruction, I need 4 bytes to send, because I must toggle the enable bit, because only one command is enabled when the enable bit is falling, I think. No? So next is to put the display on. And now you already see the on the chip that begins to blink because the display is on now. Then I send a command that the cursor is direction right, because it can, for example, for Arab letters or Hebrew letters, it can move the direction in the other right side, and moves moves the cursor to line start. Okay, after power off, normally the cursor is already to line start, but I can explicitly do that. And now I send the letter H to it when it is sent. So yeah, it worked. Maybe it's not sharp enough. Oder? I will try to make it somewhat sharper. Yeah, with fantasy you can see that this is an H. And now I go to the continuously demonstration, because now I send a sequence of various letters. So we will see finally the word hello, and then it goes to the line start again, and then world also. This takes maybe 1 minute, but yeah. Hello, yes. Now it will clear the display and start again. Now it's world with it. Yeah. And maybe, I don't know whether you see it here, it's always blinking 1 bit. This is the enable bit, because we always have to send enable to the chip, because you can send to the LCD module the bits in various different times, but only when the bit pattern has reached the correct state, and then you make the enable, you toggle the enable bit, then the data is put into the LCD chip. So it starts again with hello world again. Mm-hmm. Yeah. So this was this demonstration here, and now I want to make show you that that one can. Maybe I show first how this works a bit. So the software is like this, that before even. Yeah, also I had to, as a preparation, I had to make starting I2C, and this will put the data lines 2 and 3 as, also export them to the directory, and we receive as a response this directory content with the GPIO 2 and 3 lines enabled. And the next thing was that I started the server 8888, which has is a very short script. And on the computer side, one procedure is the procedure Raspberry text, which is a web client that will send commands to the Raspberry Pi. And one communication is, for example, Raspberry source data low. Then it will carry out the program SDA low, which is just we open this is class GPIO, GPIO3, direction right, put it as an output, flush it, put then the level low to it, close, and this makes the data line low. And we also can read the data line by set Antwort or set response, Raspberry source read SDA, and the reading of the SDA is done by that. So the Raspberry will, as a result, send a 0 or a 1 back to the computer where I run the demonstration, and the computer can find out the real state of the data line. Yeah. And okay, this demonstration is very, very slow, as you have seen, but it can really show every bit how the data is transformed. But I have also written some procs to handle fast data transfer. And this has init, start, stop, sender, the send, receive, and make acknowledge, send and make non-acknowledge, and finish. These are the subprograms. And I will demonstrate now the fast procedure. I must open the interface. It is Li²C schnell. So this is the source code from that. Has maybe 5 kilobytes or so. Yeah. And when I send it, then now you see that these bits are relatively fast blinking, and also it changes between the two chips. And after a while it makes a calculation of the result. So in this case I had 4,128 communications. So one communication is that address a chip, send a bit pattern to it, or receive something. And so it was an average 317 communications per second. So by a 100 kilohertz bus speed, you would estimate maybe 10,000 communications per second. But my program is really written in EuroTcl, so it is not that fast. But when you, for example, use the LCD, you can also make it quickly. LCD schnell. This is a program now which will put the LCD fast. I have to restart LCD, and so no. Geez, okay. Now I have to send this. Hope it works. Geez. Now you see that it's really, the LCD display is also quite fast. Yes. Also, yeah, then I come to the last thing. Yeah, this is I can also use the this no. Wieso geht er? Ach, ja. I can also use the SPI bus with EuroTcl, and here I will program 80 tiny 85 microcontroller with the SPI bus, and this I have also a demonstration for it. Spi Demo. So again, I have to move the camera a bit. So I move the camera so that it shows these pins here because in case of the SPI we have 3 outputs. This is a serial clock, master out, servant in, and there's the reset pin that must be normally high when the chip is running a program, and it must be low when you program a chip. And this can be seen now also in this demonstration mode. And finally, when the chip is programmed, then you will see a blinking diode. So okay. Maybe first with the SPI bus, in this case the signals are low all, and also the reset has been set to low, and when I send bytes to it, I have always sent a sequence of 4 bytes, then oh, it doesn't work. Because normally chip also, vielleicht muss ich das dann wieder ziehen. This is demonstration because the chip must respond. We start. SPI Demo. Shit.
So maybe
yeah.
I check this and you can show it in the coffee break to those who are
yes.
interested.
Maybe I only show this one slide here. No, no, even the PDF file doesn't read. Yeah, maybe I show this in the coffee break. This is a good idea.
Just one question, maybe. That long wire that you have here, is that a pair of wires, or is it?
No, it is 4 wires. It's the power supply, minus and plus, and then the SDA and EuroTcl. I only wanted to show by this that you can use the I2C bus also for several hundred meters if you like. It's only that maybe you have to slow down with the clock rate then. Also really it should work. So unfortunately the last experiment didn't work, but I tried in the coffee break. I didn't do the preparation for the bus, that's why it doesn't work. But I have to show now.
Now you can show it in the coffee break.
Yeah, I do that.
See it better if they
Yeah.
stand alone.
Yeah.
So are there any questions to Uli?
Seems not.
Like
Yeah.